we're Design Team 9, Justin Flynn, Katie Mahowski, Rachel Davon, Chris Basinski, and we're going to be presenting on wireless mesh networks and the ZigBee protocol. It's pretty much the basis from our design project. So our outlines, what we're going to be talking about today. We're going to start with networks in general. You know, what is a network, how they work, and topologies. So the different ways in which you can organize the devices in your network to optimize what it is you're trying to do. We're going to talk about wireless and wired networks and the different things you have to think about and work with when using wireless as opposed to wired. We're also going to talk about protocols, the rules you have to follow to make sure that everything communicates correctly. IEEE standards, their role in making sure that devices from different manufacturers all work the same. And then we're going to talk about the ZigBee protocol itself and some certified applications, their focus areas that ZigBee is used for. So the definition of a network is an interconnected system of things or people. So everyone uses networks every day without thinking about it. You know, your group of friends and family is a network. We're talking about communication networks here. So we're talking about moving data from one point to another to solve some kind of problem or to relay information. That's why the picture here is actually a graphical representation of the internet, probably the most famous network out there that we use pretty much every day now. So there's network topologies. This is how you're going to organize the devices within your network. There's many different ways to do it. They all have their own benefits and downfalls, such as like a line, you can just daisy chain things all together. They can all talk back and forth, but if you cut one of those links in between, now you have two separate networks. Or like a ring has redundancy. If you were to break like this link here, now you can just send all of your packets and all your information the other way around the ring. It's kind of application specific too, depending on what you want to do. The different topology will benefit for you, such as like a bus. If you have one channel there that everyone's sharing. So if you send something onto the network, everyone receives the same thing. Now I'm going to talk about mesh networks and why they're important. So a mesh network is a topology, like I mentioned. It's just a way in which you get all of the nodes and the devices in your network to talk. They collaborate together, so if you're sending data, like a packet, there's little bits of information in there, so a node knows if this is destined for me, I can pass it up to my application. If it's not, it knows that I can send it off to someone else so it can get where it's destined. A big part about mesh networks is also that they're self-healing, which means that new nodes can jump onto the network and start communicating, as well as drop off the network without affecting the overall process. And I'm going to pass it off to JD to give a little bit of an example of how that works.
Hi everyone, I'm JD. So here's a little visual thing of just mentioning. The nodes start off here. Very first thing they do is establish communication with each other, so that they all know that each other exists in the span of the network. So if a node wants to communicate with another node, it knows that node exists. It has two ways to get there. It can either do like a routing thing, like in your computers with tables and knows the closest neighbor and the next hop to get there, or it can do a flooding algorithm where it just sends its data across to everyone in the network, and then that forwards on to everyone, and that goes and eventually to the destination. So moves down by sending the data down to the closest node, then it goes to the next node, and then finally reaches the destination. So you're able to take in a new node, and that establishes connections, and then the network is now aware that a new node is entered, and the entire topology is there, and it adds that as a new outlet to send data through if it needs to. And reversely, you can take a node away, and the network becomes self-aware that that node is now left, and that it is no longer able to use that node to send data through. So the advantages and disadvantages of mesh networks. Advantages: reliability. As you saw, there was some redundancy there in some of the lines, so that the network can go through multiple paths to get to the destination. So if a node fails, you're still able to get your data through because of one failure. Another advantage is adaptability. So as you saw there, if you remove a network or add one in, the network adjusts and is self-aware of everything else that's going on in the network and accordingly. Disadvantage actually plays off the advantages. The overhead there to deal with removing and adding networks, there's a lot of additional logic that needs to be implemented to be able to handle that. And then initialization, starting off that network, you saw the connections appear there. That was instant, but in reality it takes a while for the network to realize every other node in the network and the span of it, and these network nodes are able to move around. So that's another thing that has to take into consideration. Wireless versus wired networks, since we're doing a wireless versus network, some of the considerations there for the wireless is beam access control. So if you're using the airwaves, you have to worry about competing signals and interference there, while if you had a wired network, you obviously wouldn't worry about that. You'd have, it'd be contained in your wire. And then security, if you're sending wireless data, obviously it's able to be intercepted by anyone that has a receiver for it, while the wired is, you have to tap directly into that line to get the signal. Physical equipment, obviously wired has wires, so you have to deal with the equipment there and maintenance for that. And then speed and reliability, wired networks tend to be faster than wireless networks and more reliable in getting the packets sent. There's sometimes loss and noise interference with the wireless network. So a little bit of an introduction to protocol. Those of you who don't know what protocol is, it's basically a contract of communication. So when those nodes got established, they need to be able to communicate with each other without messing up. And the perfect example of this is like speaking on a phone. When you call up your friend, you don't pick up the phone and say goodbye. Your friend will be like, what's going on? And you don't just start talking at the same time because you understand each other. So you begin with hello, hello. You say your message, they say their message, and you get whatever data you need to across to each other, say goodbye, goodbye, and hang up. So it's just a way that the data can, it's just a set of rules to follow, so that data gets communicated efficiently and effectively. So with that, I'll pass it over to Chris to talk about standards and specifically the ZigBee protocol.
IEEE has a number of different wireless communication standards. Well, actually, there's a bunch of standards, right? So what happens is whenever you want to make a wireless standard, or whenever you want to make any standard in general with the IEEE, the first thing you do is about 10, 15 years before you write your standard, you go find a university to hire you, get a few grad students, and get a lab to implement some kind of test bed system. You write a paper on it, try to push it through either MobiCom or MobiHawk, and you try to find some people to fund you, and you research it for a while, and eventually you get some kind of team that'll come up with some kind of bunch of consensus about whether the way you actually want to communicate is good or whether it's bad. And if it's good, and it's very seldom viewed as good by everyone, so there's a bunch of changes that go through the works, and eventually what happens is you get this kind of rough draft of some document that says, if you either want to make some device to actually be able to communicate with other devices that implement this shared protocol, then they all have to behave this certain way. And so what happens is first people, write down a specification. It goes through an extensive review process. People actually try implementing it in usually an operating system like either like Linux or Tiny OS, some embedded systems. And a bunch of people kind of get some idea about whether this is going to work or whether it's not. And then it goes through a ratification process. People actually start implementing it in the real world. And then everybody who actually wants to conform to the standard has to live with whatever's in the document. So basically what happens is they choose a number. And as I said, there are some hierarchical numbering standards. So the actual communication networking standards were 802. So these are things like 802.1, 802.2. 802.1 is a very broad standards document that kind of describes the purposes and kind of overview of the theory behind networking in general. 802.2. This is more just kind of like assignment to what's actually going on in terms of addresses, physical like layouts and structures of the networks. And then they get into more specifics up to 802.11 is Wi-Fi. That's basically wireless, kind of like LAN, except it uses a little bit more collision avoidance, which is basically if you want to talk on the network at the same time, and you have two people speaking at the same time, how do you avoid that? And if it happens, how do you deal with it so you can actually end up communicating without colliding infinitely? So there's something called exponential backoff. It's kind of we wait a little while. 802.15 is what's called personal area networking. These are just small networks that are intended to basically be used for kind of around your own kind of peripheral space around the human body. Typically things like these devices you wear on your head that communicate with your cell phone. 802.15.1 is Bluetooth. 802.15.4 is ZigBee, which is what we're working with. And the next is so the ZigBee protocol. ZigBee protocol is kind of like a very high-level replacement for TCP/IP. So TCP/IP is it's what you have in a computer that does most of the normal communication. So if you have there are a few problems you have to think about if you have a computer and you actually want to talk to somebody else. So what happens? How do you use the internet when you use a computer? What you do is you open a browser on your computer, or you open a program on your computer like Skype, like Google Chrome, or Internet Explorer, something like this, and somehow the data that you type actually goes through, down to the line, goes across the network, comes back and comes back up. But how do all of the things that get sent through your computer and the data that comes back to them, how do you know that some little few bits of ones and zeros actually correspond to the Google Chrome browser running on your machine rather than the Skype running on your machine, or rather than some other application like Norton Antivirus or something like that? One thing that does that is they have these little things like ports, and they have these other things like sessions and things like that. But there's not a lot of, that's a lot of millions of lines of networking code, they're pretty expensive components in terms of analog modems and things like digital parts to actually implement this in hardware. But on embedded devices, we don't really have, we don't actually have the real estate on the chip to actually implement this hardware functionality, and also don't have the space and code to have all this complex infrastructure. So what happened was, a few years ago, a bunch of people got together. Most started out as a bunch of researchers, and eventually it started out as also some industrial people. They got together and developed a standard to actually communicate using a wireless standard that was based on just research done, what's called ad hoc, what's AODV, so ad hoc on-demand distance vector routing. So that basically uses each node and kind of discovers the path as you route data through it, and basically using this kind of lower level kind of ad hoc communication mechanism to be implemented on embedded devices that will kind of replace what you have on your actual computer. And so ZigBee kind of takes all the other parts of the computer that are like all this TCP/IP niceties, and replaces all of that with one big chunk called ZigBee. So it does all the TCP/IP, all up through the other parts of the application layer, which is what your actual code uses, and replaces that with ZigBee, which is just kind of a lightweight application layer. Right, it's running in, ours is running in 915 megahertz, and the distance is about 10 meters. You can actually get it much higher than that, but it's mandated by the FCC based on power usage. So I think that's